Hi all, welcome to another session from Nairo Research. I'm Srijit here, and today I'm going to focus on parameterization module in AMS. So, params in AMS is a powerful framework designed for the systematic development, optimization, and validation of deterministic models such as reactive force fields, semi-empirical Hamiltonians, and machine learning potentials. So, its core purpose is to bridge a gap between high-level preference data from quantum chemistry calculations of experiments and efficient large-scale simulations, enabling accurate modeling of complex chemical and material systems. So, by providing a unified environment for data management, optimization, algorithm, and model assessment, PARAMS ensures reproducibility and scientific rigor in parameter development. So, one of the most prominent scientific applications of PARAMS is the reactive force field parameterization. So, reactive force field um, are essential for simulating bond breaking and formation in systems such as combustion chemistry, catalysis, corrosion, battery materials, and biomolecular reactions. So PARAMS allows users to fit reactive force field parameters against the reference DFT energies, forces, geometries, reaction barriers, and charge distribution, ensuring chemical transferability across different bonding environments. So this capability is especially valuable for studying complex reactive process at a time. And which is inaccessible to ab initio molecular dynamics. So PARAMS also plays a key role in the development and refinement of semi-empirical methods, particularly DFTV and XTV like Hamiltonians. So these methods are widely used for large biomolecules, soft materials, and nanostructures where full DFT calculations are computationally prohibitive. Using this kind of parameters, it can be tuned to reproduce quantum chemical reference data such as optimized structures, vibrational frequencies, and relative conformal energies. This enables accurate simulations of protein ligand interactions, organic electronics, and molecular self-assembly with significantly reduced computational cost. So in recent years, PARAMS has become increasingly important for machine learning interferometric potentials of MLP training, a rapidly growing area in computational chemistry and material science. By fitting ML models to high-quality DFT datasets, PARAMS facilitates the constructions of potentials that approach quantum accuracy while retaining force field level efficiency. So these MLPs are applied in material discovery, phase transition studies, defect dynamics, surface reactions, and mechanical property predictions, enabling simulations of thousands of to millions of atoms with nearby ab initio real level. So another major strength of PARAMS lies in the robust validations and sensitivity analysis tools, which are crucial for scientific credibility. Researchers can divide data into training and validation set, applying to property specific weights and analyze parameter sensitivity. So let me show you this thing to a PARAMS engine to show the data. So such systematic assessments is critical in applications like catalyst screening, battery degradation modeling, and reactive transport simulations, where predictive accuracy directly impacts scientific conclusions and design. So this is actually the parameterization GUI. So basically, these are actually the way that we can enter or upload the data to this PARAMS engine. So finally, PARAMS integrates seamlessly with the broader AMS ecosystem, supporting automated workflows by GUI and Python. So in AMS environment, this one is plans and efficient execution on high-performance computing systems. This makes it suitable not only for academic research but also for industry R&D applications. So this makes it, applications including drug formulation, polymer design, energy, materials, and surface engineering. So PARAMS significantly advances multi-scale modeling and accelerates scientific innovations across chemistry, biology, and material science. So by enabling the development of reliable system-specific models grounded in quantum mechanics and experimental data. So this is actually an overview about parameterization engine in Amsterdam Modelling Suite. So in the next session, most probably we'll be focusing on one example. And from this year onwards, we are focusing on more case study oriented presentations. So right now I'm just winding up. Thank you. We will see in the next tech video. Thank you.